Hello. Okay. So, alternatively, you could consider Fourier transformation, Fourier transformed field. And that will be phi t comma x vector equals integral dp vector by 2 pi to the power 3 by 2 phi tilde t comma p to the power I p dot x. So we are Fourier transforming only along the spatial directions. And so we have a new field in position space description of the field. And then the correspondingly you have a canonical field, so that the corresponding canonical field satisfies the same equation because when you act by phi hat t comma x, you think of acting by this quantity, and this operator is going to heat up, is going to act on this state and will give you phi tilde of p, and that therefore you will get the function phi of x, which is the Fourier transform of phi tilde of p vector times t comma phi tilde. So this is Fourier transform of phi tilde p. So now given this, you see this state has the information of the entire profile phi tilde of p, and from phi tilde of p you can construct the phi of x, this function, right? So that means this single state knows about the entire profile phi of x in position space. So one could actually alternatively use a notation of t comma phi functional. So change notation give this by this. The same state has the same it has the same information. They are the same states. They have equivalent amount of information. You depict the state by the position space profile or momentum space profile. It doesn't matter. Given one other can be found. Okay. So now armed with these notations and definitions, etc., we finally arrive at a path integral statement in QFT. So path integral statement in QFT will be the matrix element between Ti comma phi, sorry, Tf comma phi f, then time ordered product of a bunch of insertions Ti phi I should be given by some suitable normalization times d phi I to f e to the power I over h bar is if of phi, and the insertions corresponding to these operators sitting here. Okay, so now that statement is being claimed for a theory. So this is true for a theory given by Lagrangian density minus half eta mu nu del mu phi minus u of phi, when this phi is actually phi of x. So u is a function of phi, and then phi is a function of both t and x, so that is a 4x, right? And this action is integral dt integral dt Lagrangian density, integral d4x Lagrangian density. When you use it here, is if will be will have a time integration which is ti to tf. Okay, that's the significance of this ia comma f. And the boundary conditions, this path integral will be all integration over all the profiles, all the paths or functions which satisfy the boundary condition that phi ti or tf x vector will be given by phi I or f x vector. So this is the four-dimensional boundary condition for the four-dimensional fields. Now, how do I arrive at this statement? Actually, it is just a direct generalization of the non-relativistic statement here, because you can just go ahead with this mathematical analogy, the way I have been developing all the definitions and so on. You can it's another another statement which shows, which you can arrive at by exploiting the mathematical analogy, right? I mean, so one method will be to discretize, think of it as a discrete system instead of the difference between this system and this system. The QFT system is that x is analogous to a field, entire field. X is a mechanical degree of freedom, and on this side you have a field. So field has infinite number of degrees of freedom. X is single degree of freedom. This has infinite number of degrees of freedom. There is formally you can extend expressions in terms of x's to expressions here, which has been which I have been doing. But as I have mentioned, I guess in additional note 3, that there is a more precise way of understanding this is to think of the three-dimensional momentum space as a grid. So you are latticizing the continuum three-dimensional space into a you are latticizing it to a three-dimensional grid. So then so the problem in translating from here to here, going beyond the formal analogy, is that it is not countable. It's an uncountable set of degrees of freedom, which is infinitely many, but still it is infinitely many but uncountably infinite. So that is one challenge. So you make it countable by discretizing the space, exactly what we did in defining path integral. The path integration was made, the problem was that it was the degrees of freedom that over which we are integrating are uncountably infinite. So we made it countable by taking the time slices. Similar thing you can do, you can put a momentum space lattice, and then it becomes a countable number of degrees of freedom, and some total number of degrees of freedom will be n, and there will be a lattice spacing, and you can, at the end of the definition or whatever statement you want to arrive at, for example, this path integral statement, once you arrive at this, then you basically have, for discrete momentum, for each discrete momentum, you have an integration. Those are path integration, but because for each discrete momentum, it's a path in terms of t, time as a parameter. That's a path. So that's still a path integral. But you need to know how to write the action for the discrete version, in the discrete version, how to write the action and so on. So you could do that, and then after arriving at this statement, then it's just a multi-degree of freedom generalization of this statement. This statement is made for only one single degree of freedom, and you can just generalize it to a statement for multiple degrees of freedom. And then you send the number of degrees of freedom to infinity in a particular way, where the lattice spacing goes to 0 and the total number goes to infinity. Okay, and that is how you arrive at this expression. So it is basically the, in spirit, it is basically the same statement as this one. So we will take this as a path integral statement, and of course we, as we mentioned, that this is a mathematical theorem. Like, this result holds if you have a time evolution operator given by this Hamiltonian, and on the right hand side action is given by this. And therefore in the field theory side, according to the mathematical analogy, you will consider a Hamiltonian corresponding to a Lagrangian whose density is given by this. It is the same form, because eta 0 0, our signature is -1, mostly plus, so eta 0 0 is negative, so that is phi dot square, half phi dot square. It's a kinetic term of, with mass m equal to 1, and then the rest, which is minus gradient phi square, half gradient phi square minus u. So half gradient phi square plus u is the in total potential, if you would compare with this. Okay, so so this is the same structure of the Lagrangian, and this is basically using the mathematical analogy. Now let me make some comments regarding this. Now I'm going to interpret this statement in the light of field theory. So those are the comments that I'm going to make, and various aspects of these comments will be unfolded or studied in detail more in later stages. Okay, so but right at this point, given the understanding that there is a similarity as far as the process is concerned, there's a similarity of this statement and the physics associated to it between that and this one. So exploiting that similarity, we will make some comments. The detailed study of those, some of the aspects will come later. So first of all, this path integral should be calculated either by Euclideanization or following I epsilon prescription. And then number two, this matrix elements can be computed by expanding the action around the classical solution, as we have discussed multiple times earlier. So matrix elements can be computed by expanding the action functional around a classical solution. Now, after expanding around a classical solution, if you want the resultant theory to be Lorentz invariant, then what kind of classical solution should one choose? A Lorentz invariant, Lorentz invariance will be preserved So Lorentz invariance will be preserved if phi lower bar, the classical solution, say phi lower bar, if phi lower bar is Lorentz invariant, if the solution breaks Lorentz invariance, right, then the physics around that solution will also be Lorentz non-invariant, and the phi lower bar can be Lorentz invariant only if it is constant. Phi lower bar t x vector is equal to a constant phi. Okay. In order to find that curly phi, which is the constant value, what you could do is to write, so this must satisfy the, you could take the potential u, potential is a function of phi, which is a function of x, and that's a value of the potential for field theory. But what you can do is to replace this phi of x, once you know that the classical solution is a constant, you replace this by curly phi, and then the solution to this equation, curly phi should be solution to this equation. That's an extremum, that's a classical solution. And this just says that just as in the ordinary classical mechanics, this classical solution, this corresponds to an equilibrium. This is an equilibrium situation. That condition is an equilibrium. If it's a local minimum, that means double derivative of u at that value of phi is greater than 0, then it's a local minimum, and then that means it's a stable equilibrium. And a local maximum would mean that del squared u of curly phi is less than 0, and that means unstable equilibrium. Now, in this field theory, in the context of quantum field theory, what does this curly phi mean? So the curly phi characterizes vacuum of the theory. When you do the canonical quantization, that is the minimum energy state in that canonical quantization is a vacuum state. So that is characterized by phi. So phi characterizes vacuum, which is the minimum energy state in canonical quantization. Vacuum of the theory. So suppose you have a profile like this. So let me take an example. So this is a maximum, local maximum. This is sort of a minimum here. So this is phi, and this is another local minimum. And so let me call this phi 0, which is lower, the value of phi, the value of u is lower than this local minimum. So this is a more stable vacuum than the other ones, and this in fact is an unstable vacuum. So one can choose to study the quantum theory in a particular vacuum. Say given by phi 0, then the path integral can be written in terms of shifted field and potential, which is the shifted field is, say, chi is phi minus the vacuum value phi 0. Okay, so chi measures the shift from this. So you're looking at a vacuum, you are looking at a theory whose vacuum state corresponds to the system sitting at this minimum, and the fluctuation of the field which takes part in the dynamics around this vacuum is chi. Okay, and then you define a shifted potential V of chi to be u of phi. Phi is chi plus phi 0 minus u of phi 0. So in terms of V, it will look like so V versus chi will look in the following way. So this is your V of chi, and chi is 0 at this value. Not only that, the minimum has also shifted. So this has become 0. This is how it looks. So which means now in terms of chi, the potential is not only minimum at chi equal to 0, but also the value of the potential is 0. Here, if you work in terms of phi, the difference between u and v is a constant shift of the potential, then you are allowing this much of vacuum energy, and a field theory such an energy will produce an infinite amount of energy. We will see why. In a finite degree of freedom system, it is only that much of energy difference between these two potential, but in a field theory context, that it will add up at every space point to give you an infinite amount, which is a constant piece, and that better be subtracted off because it doesn't contain any interesting physics there. There is no physics in that constant piece of energy, so you subtract it off from the definition of the potential. So this is a more satisfactory and more convenient picture to work with, and then you could consider path integral in terms of chi and in terms of v. So how does that look? Let us see that in the next slide.